In this session, I will solve questions related to topic waves and the properties of the waves. Question 1. Which of the following does not apply to sound waves? Which of them property cannot be applied to the sound waves? What could be the answer for question 1? So sound waves are longitudinal, that's true. They result from vibration, they transfer energy, but these sound waves cannot travel through vacuum. They required a medium to travel. Without a medium, the sound waves cannot travel. Question 2. Two coherent source. Coherent means like the two sources, they maintain a constant phase relation. Means every time if one source is emitting out crest, the crest is coming out the other one also. There is a crest. So two coherent sources emits wave of wavelength lambda. At a point where the two waves meet, there is a phase difference of 90. Which of the following could be the path difference? If the phase difference is 90, like if we represent say two waves to show that they have a phase difference of 90. This is one wave and this is another. So what is the difference in terms of path? The path difference between the two waves. In terms of wavelength. A, B, C or D. So when we produce it backward, so how much wave we have to produce backward? We have to produce only the quarter of the wave. So the part difference between them is lambda by 4. If we have to produce half of the wave, like basically in terms of part difference and phase difference, if the phase difference is 0 and 360, lambda to lambda, this also because constructive interference, so 0 or 360, lambda by 2 means 180 or pi, and lambda by 4 means, because lambda by 2 means like crest joined with a trough, so 180 or pi, and lambda by 4 means 90, or we can say pi by 2. So this is in terms of, this will result in a complete destructive interference, but in the question they mentioned a phase difference of 90. So when the phase difference is 90, the part difference will be, in terms of wavelength, the difference will be lambda by 4. Is it clear, this question? Four diagram shows waves of different wavelengths approaching a slit of different widths. So slits having different width. In which diagram the diffraction is greatest. For diffraction to be maximum, the condition for maximum diffraction when wavelength is approximately equal to the gap size. So when the wavelength is approximately equal to gap size, we'll have a maximum diffraction. So if we measure this wavelength and the gap size, you will find both are same. So we'll observe maximum spreading. So B is the right answer. Question 4. When a fire engine moves away from the observer, the pitch of the siren heard by the observer decreases. This is because this is related to Doppler effect. You have a source, the fire engine. This is a source which is producing a wave and it is moving away from the observer. Like this is observer and it is moving away from the observer. So what happened to pitch? The wavelength increases. So what happened to pitch or the frequency? So pitch of a siren, the frequency increase and the wavelength increase and the frequency decreases. But what about the answer when you check the options? The wavelength of a sound wave decrease, that's wrong. The speed is not changing. They did not specify this. Now two options are there. The frequency of the siren decreases, the distance traveled by each wavefront increase. So as the pitch increase, basically what happened as the pitch is decreasing and the wavelength will increase. So what we will observe, we'll observe the frequency will also decrease. In question 5, the diagram shows a shape of a wave on a surface of a tank of a water at one instant. The wave is traveling to the right, so wave is moving towards the right hand side. On the diagram, mark a point on the water surface so mark a point on the water surface to show the motion exactly 180 out of phase and with the motion of x. So with reference to x, we have to mark another point which is 180 out of phase. 180 out of phase means like if one point is at crest, like example, see, if x was here at crest, the y will be there at trough. When we move x, so what will be the new position? X will be here. Because this x and x dash or x and y are out of phase because one is in the crest and the other one is in a trough. So when x move a bit, the 180 out of phase are there. So x is now at this position. What will be the new position of the y which is out of phase? So it will be at this new position. This shows like if you want to mark a point which is 180 out of phase. So this is a point which is 180 out of phase and we have to label that as A. Draw an arrow at a point Y to show the direction in which the water at Y moving at an instant shown and mark on the water surface what that is at a red shown, label that point as D. So basically it's a continuous wave. So as the continuous wave is moving, the water waves are continuously moving. So when we want to show the continuous wave or motion of the continuous wave, so how we can represent that? Like this is the first position, then new position of this wave will be like this. And so on. So you can clearly see that what happened to X and what happened to Y. The new position for X, it will be up, and for Y it will be down, because as a wave is traveling, the wave is moving, so it's a continuous wave. When it's a continuous wave, if I show the new position of the wave as it will travel, so the position of the X will change, X will rise, and what happened to Y? Y will move downward. So we have to show by an arrow that the direction in which the water at Y is moving at the instant shown, and mark a point on the water surface that is rest and label this point as B. So which position it will be at rest? The peak position, the extreme position, like example, you can mark anywhere you can mark, but on the extreme position. Because that moment the particle will be at rest. Because that's the maximum position where the particle can move. It cannot move more than that. So you will, on a continuous wave, you will mark a point, the extreme positions, as the position where it will be at rest. Is it clear, this question? The next question, a student look at sunlight reflected of a puddle of water. She puts a polarizing filter or a polarized filter in front of her eye. She rotates the filter and the puddle appear to be darker and then lighter. Explain this observation. So basically what happened, as we know that the polarization can happen when the light is passing through a polarizing filter or the light is reflected from the water surface or any surface. But when it is reflected, it is not completely polarized, it is partially polarized. So light, first thing, the light which is coming from the sun is unpolarized light, having many planes of the vibration, and these vibration are perpendicular to direction of propagation. But when this light strikes the surface of the water, the puddle, it will be partially polarized. So when it is partially polarized means most of the component are absorbed, some components are still there. That's partially polarized. But as the student is looks at the sunlight which is reflected of the puddle using a polarizing filter, so as he is rotating a polarizing filter, it appeared to be bright, lighter, then darker, then lighter. What is the reason for that? When the plane of the polarizing filter are perpendicular, so then it will be completely dark because the polarizing filter will not allow that light to pass through. And when the plane of the polarizing filter are parallel to the light, the component of the light, it will allow that, so it will appear to be lighter. Why it is lighter? Because it's polarized, so polarized lights are not too bright, it will be a dim. So answer for this one, when you write the answer, so basically what happened, the ray of the light which is reflected is polarized, and this polarized light, it's having a vibration or oscillation only in one plane, and when it is passing through a polarizing filter, it only allow oscillation in one plane or one direction to pass. When planes are parallel, it appear to be light, but when planes are perpendicular 90 degree, it appear to be dark. Is it clear? In question 7, two students demonstrate standing wave. How they're producing a standing wave? So they produce a vibration and their vibration travel in opposite direction. As a result, it will give rise to a standing wave. The diagram shows the appearance of a standing wave on the rope at one instant, each part of a rope at its maximum displacement. Mark a position of one node on the diagram and label that as N. So how we can show the node? Because basically as it will produce a standing wave, this is how it will produce a standing wave. So maximum displacement is called antinode and the minimum displacement is called node. Then antinode, then node. But we have to just mark only one node on the diagram. The next part, arrow at point X shown the direction of the vibration. Look, in a standing wave, the particle tend to move towards the mean position. So we have to draw an arrow to show the direction of motion of particle at Y and at Z. So at Y it will move towards the mean position, so it will be upward arrow, and at Z it will be again downward. The frequency of a vibration shown in the diagram is 1.5 Hz. When a rope is vibrating with fundamental frequency, there is one antinode. Calculate the fundamental frequency. Basically, this is vibration for how many, the frequency for how many nodes? 1, 2 and 3. And we have the formula that Fn is equals to NF1. F1 means the fundamental frequency. When it is vibrating, when the same rope is vibrating in one loop, we call that as a fundamental frequency. So Fn for 3 loops, the frequency they already mentioned when it is vibrating as in the figure as shown, that is 1.3, 1.5, sorry. So if 1.5 is equals to 3 times F1, but we need F1, so F1 will be equal to 0.5 Hertz. That is a formula which relate the frequency of a standing wave in a string, that the fundamental free or n Fn is equals to Nf1, or fundamental frequency is number of frequency of n loops divided by n, so we'll get the fundamental frequency. Noise cancelling headphones were first invented to cancel the noise in aeroplane and helicopter cockpits. They work usually using a principle of superposition. Sound waves can enter and pass through the headphone and are detected by the microphone. Electrical circuit send a signal to the loudspeaker so that it produces an opposite wave, and compare the property of the two sound waves to produce a complete cancellation of two waves to reach the air. So basically what happened, the sound wave, this is sound waves are longitudinal, but this is a representation only as a transverse to explain the idea. Sound waves are coming from the engine. So when the headphone receives those sound waves, it produces an electrical signal and produce a wave and send it in opposite direction. So what is the characteristic? Because we want to cancel out each other, means we want the resultant to be zero, or we want to produce a node. So if we want to completely cancel out each other, first thing, because for completely cancel out the wavelength, the frequency should be same for two. wavelength, frequency and amplitude should be same. They should travel in opposite direction, and they should be 180 out of phase, because when they are 180 out of phase, like if the crest join with the trough, they will cancel out each other. So the characteristic to cancel out the signal, they should have same frequency, wavelength and amplitude. Travel in opposite direction. (180) out of phase. So these are the characteristics, these are the properties which these two sound waves must have to completely cancel out the effect of each other. Coherence means when source is producing, every time it is producing a same pattern of vibration, we call that as a coherence or coherent. The source every time is producing a same pattern of a wave. In practice, the incoming sound is reduced in volume rather than cancelled completely. Noise cancellation headphones work well when the noise is from the jet engine. They are not very effective to cancel the speech or the music. Why it is this? Because the sound which is coming from the engine is actually a continuous sound with a same frequency, constant frequency. But music or speech, what happened when we are, even for a singer example, when a singer's, as is saying, so what they produce range of frequency, like high frequency, then even the amplitude is not constant. So it is difficult to cancel out this sound or produce, because amplitude is also changing and the frequency and the wavelength is also changing. So why in practice it will be difficult to cancel out the speech or the music sound as compared to the sound which is coming from the jet engine. So the sound which is coming from the jet engine, it's having a constant frequency, amplitude, but the sound which is produced by the speech, it is a variable frequency, variable amplitude. That's why it is difficult to match the signal to cancel out each other. So this will be difficult to cancel out the sound which is coming from the uh, music or music sound or speech. In the question, a sonic tape measure uses ultrasound to measure a distance in the building. It will send out a pulse, ultrasound travel towards the distance wall, and then it bounce back. Record the time interval between the pulse being sent and returned. For a one particular measurement, the time interval was 25 milliseconds. Into this 25 into 10 to the power minus 3. Calculate the distance from the sonic tape measurement to the wall. Speed of the sound is given 330. So whenever there is a reflection, we use the formula speed is equals to 2 multiplied by distance divided by time. Because that the wave travel and then return, so traveling distance d, coming back d, so speed is 2d divided by t, so we need this distance, so it will be speed multiplied by time divided by 2. Speed is given 330, the time interval is 25 milli, so 25 into 10 to the power minus 3. Now that's divided by 2, so 330 multiplied by 25 exponent minus 3 and divided by 2, so what's the answer for this? 4.125. 125 meter. Why is ultrasound transmitted in pulses? Like why we are not using a continuous wave? Why we are using a pulse? So as we discussed this, the reason for using a pulse, so one pulse must be sent before the next one is sent, or basically the two pulses which are traveling, they cannot overlap with each other. There is no interference of the pulse. Otherwise, if we are sending a continuous wave, the wave is going and then hit the surface and bounce back. So there will be interference of the wave. So to avoid interference, we are using a pulse, not the continuous wave. Because if interference occur, then maybe we will lose the signal as the two waves might cancel out each other if they are anti-phase. Question 10. Which of the following statement about the standing wave is not true? So when we make, like example, the two waves combined give rise to standing wave. Particle between the nodes oscillate with varying amplitude even at node. Particle between the adjacent node, like this is one node, this is another. So particle between the adjacent node, they have varying amplitude. That's true. Like example, if I say particle A, particle B, particle C, D, E, they have different amplitudes for them. Amplitude means maximum displacement which they cover. So you can clearly see their amplitude is different. Amplitude is the distance from mean position to extreme position. So A is true statement, is not wrong. Particle between the adjacent node are moving in phase with each other. Yeah, they are moving in phase, like they are moving in the same manner. That's true. Particle immediately either side of antinode are moving in opposite direction. That is also true. Like example, if you have a node here, if this particle is moving up, the other particle will move down. So that's also true. The particle undergo no disturbance as antinode. The particle at antinode, the maximum displacement is there, so they undergo a disturbance. It should be no node here. The particle undergo no disturbance at node. Then it will be true. But they mention antinode. Antinode is a maximum displacement. So without movement of particle, how they can have no displacement? So D is the right answer, which is not a true statement, because they are asking which statement is not true. Is it clear? In question 11, a cathode ray oscilloscope can be used to show how the displacement of a wave vary with time. Each square represents 5 milliseconds. What is the frequency? First, you should get the time period. Time period is 4 box multiplied by 5, so 20 milliseconds. Or 20 into 10 to the minus 3 seconds. And time period frequency is reciprocal of time period. What's the frequency? F is 1 over T. Question 11. What could be the answer? So B is the right answer. That's 50 hertz. A source of a sound moves away from observer steadily, increasing speed. Compare with the original sound. The wavelength reaches the observer will be like you have a source and you have observer, and the source is moving away from observer. So compared to the sound when it was stationary, and it is also accelerating. What could be the answer? What happened to compare with the original sound, the wavelength? So wavelength, first thing, because it's moving away, so wavelength increases. And because it is accelerating also, the distance between the wavelength, the wavefronts will also decrease, and it is continuously increasing. Question 13. If you look into a fish pond on a bright sunny day, you sometimes cannot see the fish because of the glare of light reflected off the surface. When the sunlight is reflected off the surface of the water is partially plane polarized. State what's the difference between plane polarized and unpolarized light. So the difference between plane polarized and unpolarized light, its vibration is in many plane, whereas for polarized light, the vibration is only in one plane. Unpolarized light is having a vibration in many planes, but polarized light is having vibration in one plane only. Explain how a Polaroid sunglasses can enable the fish to be seen. So basically what happened, the light which is coming from the sun, that's unpolarized light. But when it is reflected, the light is reflected, it is plane polarized. So if we have a polarizing sunglasses, So if we are having a polarizing sunglasses, it will stop the reflected part as it is perpendicular to the polarizing filter, and the light from the fish, we are able to receive that. How we are able to receive that light? Like this is the water surface. The light which is coming from the sun is unpolarized light, means having many vibrations in many plane. Which is perpendicular to direction of propagation. So light is which is reflected, and some of the light is refracted. And we have what? We have a polarizing filter, the sunglasses. And only one component they allow. So light which is reflected from the surface, it is horizontally polarized. An example, the light which is refracted is not polarized. So what happened? It will block the component which is perpendicular. So this component which is due to the reflection will not receive. And a polarizing filter only allow one component to pass. So vertical component is able to pass here. So it means we are able to see what is underwater but not the reflection at the surface of the water. State why sound waves cannot be polarized. Sound waves are longitudinal waves. Longitudinal waves, their direction of vibration is parallel to the wave direction, so that's why it cannot be polarized. It has already oscillation in one direction, and that direction is parallel to wave, that's why it cannot be polarized. Frequencies below the audible range of for human are called infrasound. Infrasound is produced by earthquakes. Describe how sound waves travel through air. So what happened? How these sound waves travel through air? So sound waves are longitudinal waves in which the particle vibrate parallel to direction of wave, and it travel through a medium by compression and rarefaction. So it travels through a medium by a series of compressions and rarefactions. What is meant by the term frequency? The term frequency means number of vibration in 1 second. Infrasound has a wavelength of 1500 meter, and the frequency 2. What is the speed? So you have the formula V is equals to F, lambda frequency is 2, and the wavelength is 1500, so that is equals to 3000 meter per second. In 2004, a huge earthquake produced a very large tidal wave which swept across Indian Ocean towards Sri Lanka. Many large animals in Sri Lanka move away from the coast before the tide waves hit. suggests a reason for animals behaving in this way. So, what is the reason why the animals behave in this way? Because animals have a different range of audible frequency than a human. So, animals detected, they have different audible range, and that infra travel faster, so detected earlier by the animal. So these are some questions related to topic waves. I'll share another link and continue this discussion.